So why do we need buffer management? Well, pretty much every computer has a random access memory that is different from the secondary storage. That is, the random access memory is volatile, the secondary storage is persistent, it's not volatile. So you want to utilize the random access memory more efficiently for your particular application. If you let the OS do it, the OS will not know what the application is doing because the OS is very general purpose. And so the DBMS has its own memory management, and its slice of memory is called the buffer pool. That's just the terminology that database people like to use. The buffer pool is just a region of RAM that is exclusively assigned to the DBMS, to the RDBMS. The DBMS or the RDBMS, I'm going to use them interchangeably for this part of the course, but there are other DBMSs that are not relational. For now, let's assume the DBMS means relational DBMS. It divvies up the buffer pool into slots called buffer frames, and each frame accommodates a buffer page. And the buffer manager is a subsystem. It's a piece of software that's a chunk of the larger piece of software that reads pages from disk to the buffer pool and writes dirty pages from the buffer pool back to disk. Dirty means some bits in that page have been updated by a particular user. And here the user means a query. And the query is basically a relational query that could be a write operation or a read operation. If it is a write operation, the page gets dirty. And then you have to update that copy on the persistent record of the data, which is on the disk. Okay, so page requests come in from the higher level of the DBMS, which basically means your queries that are getting issued. And then your page in this illustration, these are the buffer frames. This whole region is the buffer pool, it's part of the RAM. And then you have the disk controller that talks to the disk, and the database is actually a set of files that are laid out on disk. And then the buffer manager basically brings pages back and forth between the RAM and disk. And here in this buffer pool, it's mostly empty. There are only 3 frames that are occupied. The rest are free. And what is a buffer replacement policy? A buffer replacement policy is just a policy. If you recall from your OS terminology, there's policy and mechanism. Here it's a policy. It'll be implemented using a mechanism. But the policy basically tells you which frame do I evict based on metadata that you store for each buffer frame if the buffer pool is full, but you need to read a new page from this. So what are the 3 kinds of operations that the buffer manager handles? There's one which is a request for a page that comes from a query, and this could be a read or a write request. There's a release a page when it is no longer needed for that query. Say the query has processed it, and then now it no longer needs it. And then there's a notify, which is a query tells the buffer manager, I have modified some bits on this page. Okay, so that's a write operation. What is the metadata that the buffer manager maintains? In order to handle all this efficiently and effectively, there are 2 variables that are absolutely critical. Pin count, which basically tells you how many queries or how many users are currently accessing the page that is in a particular frame. It could be because multiple database administrators or data scientists use the same ratings table to calculate different operations. Like one wants to compute the average rating for one movie, the other wants to compute the average rating for a user, and now both these queries are issued to the same table on the same DBMS. So both of them can access the ratings tables pages. Pinning basically means the pin count is incremented. That means a new page request has arrived. It could mean another user has joined the system and now issued a query. Unpinning does not mean the pin count is decremented. So keep that in mind. There is no word for the page count getting decremented. Unpinning basically means the pin count has come down to 0. When a query is done with the page, it just releases it. Okay? The dirty bit basically is 1 bit of information that tells you, has this page been modified? It doesn't matter who modified it. It's just been modified, and therefore its persistent copy on disk has to be updated at some point in the future. Yes?
If a file has been set to dirty, and the user wants to use that again, do we have to write it back and read it?
Yes, that's a good question. So we will get to that. If one query updates a part of the page, and another query comes and updates a part of the page, it depends on whether there's a conflict between these 2 updates. If there is no conflict, if one query is updating one record, and the other query is updating some other record that's completely different, they can actually be updating the same thing. And as long as there's no conflict, it's allowable. These sorts of issues, like when you have 2 users modifying the same page, are handled by a mechanism called concurrency control and transaction management. We'll get to that at the later part of the course. Okay, for now, let's assume if a page is going to be modified, it's modified by only one user. Okay. Any other questions? Okay, so what is the flow chart for handling a page request? The buffer manager says, hey, I have a new page request. First thing you want to check is that page in the buffer pool? So that tells you that there is a globally unique way of identifying a particular page in your entire database. If yes, you return the address of the frame in the pool. What does the address of the frame mean? It's just the location in RAM. So you just return the location in RAM. It's a pointer. And so now the query can use that pointer, get the data laid out in that space of memory, and continue its query processing. Of course, because there's a new query that has requested this particular page, that page's pin count is incremented. Therefore, the buffer manager maintains auxiliary data structures for every page. What is the pin count? What is the frame? What is the pin count? So when you're implementing your project one, you will be dealing with all these data structures and algorithms for buffer management. If the page is not in the buffer pool, then, like I said, the buffer pool is full, but you need a new page to be read from disk. There is no empty spot, so you have to kick one of these pages out. Which page do you kick out? That is the policy. And notice that the pin count for that frame must be 0. Otherwise, that means there is some query that is actually using that page right now. You do not want that query that is using that page to suddenly boost that page. So if every frame's pin count is greater than 0, then this request is put on a wait queue. So if a new user comes in, reads a new table, but the buffer frame, all the buffer frames in your buffer pool are occupied with pages that are being used by some other queries, there is none that has a pin count 0, that query request is put on a wait queue. You have to wait until somebody is done with these processing and at least one page gets unpinned. Okay, now luckily you have found a frame that has pin count 0, and now you can use that frame to read in the new page that was requested here. But you have to check the dirty bit. If the dirty bit is set, then that page has been updated. It has to be modified on disk. That operation is called flushing. The buffer manager immediately writes that page back to the location on disk where that page was physically located. And that is a blocking operation. Okay, so this query will have to wait until this flushing is actually done. Only after the flushing is done can you now read the newly requested page from the other location on disk into this particular frame. Okay? Now, because you have a new user for the page in that frame, the pin count for that page in that frame is incremented, so it goes from 0 to 1, and now you return that frame's address to the query processor. Any questions? Does this make sense? Yes?
So is there like a spin lock or mutex for each page frame?
Is there what?
A spin lock or mutex?
A lock.
Yeah.
Yes, we will get to locking later when we deal with concurrency control. There is actually locks of different granularity in a DBMS. There are locks on entire files. There are locks on pages. There are locks on records in a file. There are locks on columns. There are locks on predicates. So we will deal with all these kinds of locks that a relational DBMS offers later on. Okay, any other questions? Yes?
So in the DBMS, I think we do queries for some, it's a table, and how do we know, or how the DBMS know which tuple is in which page?
It won't know just yet. We will deal with that when we talk about query processing. Okay, but for now, assume that you know that this is the page you want to access, and this is how it operates. Okay.
So the interface are all based on the page, which the page index.
Yes, everything that goes between disk and memory is at the page level. Even if you have to get only one record, you have to read a page from disk.
Yes.
The rest of the page is useless for you. Okay? Any other questions? Okay, cool. So everybody's following through. Let's look at the buffer replacement policy. Why is it important? It is important for one reason, reducing I/O cost. If you do not manage your buffer pool cleverly, you might actually be paging things in and out in an ad hoc fashion that increases the runtime of your query. So the runtime is abstracted as I/O cost, which is the number of disk reads or writes that you need to do. Every page read is counted as one cost. Every page write to the disk is also counted as one cost. And this is one of the key things that sets apart a relational DBMS from an operating system. The operating system has no understanding of what is called the data access pattern. How are the pages accessed for a particular query? There is a specific access pattern. It's accessed only in this way. We will get to that when we talk about query processing. That information is available because the RDBMS knows what the query is. It knows relational algebra, it knows SQL, and now it can actually predict what is the access pattern for that particular workload. And based on that information, there are various policies that relational DBMSs can employ. You can actually employ a different policy for a different set of workloads. If you have a workload that is write-heavy, you would probably want to use a different policy. If you have a workload that is read-only, you probably want to use a different policy. Even within read-only, if you have a workload that's primarily aggregate queries, you want to use a different policy. If it is very few aggregate queries, but primarily just selection queries, you could use a different policy. So we will talk about this match between policy and the access patterns later. But for now, what are the various policies? Least recently used, most recently used, LRU and MRU. Clock algorithm, which is what you have to implement for your project. It's a variant of the least recently used with lower overhead. And then FIFO, first in, first out, random, and so on. A lot of these algorithms are very common across all forms of cache replacement. There was a question on Piazza, how is this different from operating system cache, buffer cache, operating systems memory management? Well, it's basically two instances of the same thing. What the DBMS does is basically apply one of these policies based on the access patterns of its workload. What an OS does would also pick one of these policies. You could also have these sorts of cache replacement policies arising in network caches, like when you have video delivery and there are contents that you have to circulate through your network, you might want to cache popular videos locally in a particular sub-area, like a sub-network, rather than having to access a server on the other side of the world. So there are caching policies in networks too. There are caching policies for processor caches, L3, L2, L1 caches. Caching policies for GPU, graphics processing unit caches. These sorts of policies will matter there too. Okay, so these are kind of general policies, but their implication for the specific setting where they're applied differs based on the access pattern of the data. Any questions? Okay, so what is the least recently used algorithm? The algorithm is pretty simple. You have a queue of pointers to frames with pin count of 0. So it's a queue data structure. You maintain a queue data structure where each entry is a pointer to the frame in your buffer pool that has a pin count of 0. If you get a unpinned frame, like maybe query is done with a page and now that pin count has been brought to 0, then that page is added to the end of the queue. Okay? Now if you want a new page request coming in, the page is not present in the buffer pool, the buffer manager will now have to figure out a slot, a frame, to read a page from this into. It will just grab one from the front of the queue. Okay? So that means it's least recently used. The one that is at the end of the queue was the one that was most recently unpinned. That means it was most recently used, but you don't want to replace that. You want to replace the front of the queue, which was the one that was unpinned the earliest in the past. Okay, so that's why it's a queue data structure, and you basically get this least recently used algorithm. Here's a concrete example. Suppose there are 5 pages on this, and for our purposes, I'm just calling them pages A, B, C, D, and E. Okay? How exactly a page is identified, we will get to that later in this topic, but let's just say there are global identifiers A, B, C, D, E. You only have 3 frames in your buffer pool. Now clearly, RAM has lower capacity than disk. Disk could be terabytes, RAM is usually just tens of gigabytes. So in this case, it's a toy example, so you only have 3 slots. You can only accommodate 3 pages in memory. Now here's your page request sequence. The page request sequence is basically the sequence of requests issued to the buffer manager by the higher levels of the system, the queries that are issued to the DBMS. And the requests are as follows. Request A, request B, modify A, request D. What does this mean? This means the query wants to read page A first, and then read page B, and then it updates page A. So that's modify. And then it requests page D, so it wants to read the content of D. And then you have release B, which means it says I'm done with all the records in B, I don't need it anymore, and therefore it releases B. And then it releases A, saying I'm done with A, I don't need A anymore. Then request E, request C, release D, release C. Okay, so these are the three kinds of page requests that come in. One is request or just read, modify, which is update, and then release, which means I'm done. Okay, so these are the things that the buffer manager gets as input, and now the buffer manager has to manage these three frames and cache these pages from disk intelligently. So what does the LRU algorithm do in this sort of a setting? Here's your buffer pool. This is a pictorial depiction. You have 3 slots, so each thing is a frame, and PC is your pin count, and DB is your dirty bit. So these are the 2 pieces of metadata that's stored. First thing is a request for page A. You read it from disk, all 3 slots, all 3 frames are empty, so the buffer manager can just push it into the first frame. Does this make sense? So now the buffer has a page A in the first frame, the second and the third frame are empty. And because you have a page that's in the frame, its pin count is set to 1. So it gets pinned. Now, page B, so request page B, so that's your sequence, right? Now the second operation in your sequence is a request for B. What will the buffer manager do? Recall the flowchart, it looks for an empty frame. There is already an empty frame. So you can just read B into the empty frame. And you pin it. Okay? The next part of your sequence is a modify on A. So the query is now updating the page A. What happens then? Well, the frames are intact. Nothing gets read from disk or nothing gets written to disk yet. But the dirty bit for A is set to 1. Because the query has modified A, that means that page has been dirtied. Okay? Now you get a request for page D. What will happen? Anybody?
For free frame.
Yes, you have a free frame here. The buffer manager just reads D into that frame from this. Okay? Everything else, the metadata and all remain the same across these. And then you have the operation release B, which means the query is telling the buffer manager, I'm done with B, I don't need B anymore. What does the buffer manager do? It does not kick B out of the memory. B is still there in the buffer frame. The only thing that changes is the metadata for B, which is the pin count, gets decremented. And because it has come down to 0, this is basically that frame got unpinned. Okay, so B got unpinned. Everything else is the same. So you can see the dirty bits are the same like this. The pin count for A and D are still the same. Yes?
Why do we not have the valid bit?
The dirty bit?
The valid bit. That's never mind.
The valid bit?
Yeah,
Is that an
the
OS
clock-
thing?
Yeah.
Yeah.
Okay, so maybe it's in the clock algorithm. We'll get to that later.
Oh,
Okay, this is the LRU algorithm. Okay? The LRU algorithm approximates this algorithm with less metadata. Okay, so we'll get to that. For now, the LRU algorithm is the simplest algorithm you can imagine for this. The clock is an approximation of this with less metadata.
I think the point is, why do we need to count the number of times the one page uses instead of simply use a valid bit for each page? That
Exactly.
is much simpler.
Yep, that's why clock is simpler than this algorithm. Instead of counting how many users are using this page, you just see is it valid or not. Okay, so we'll get to the clock after this. Okay, so release B, notice that B is still in memory, it's not flushed to disk. You don't have to flush it to disk. Flushing to disk is an I/O cost, and that increases runtime. You don't want to spend that cost. So what is the queue of pointers? So right now, you have frame 1 in your pointer. Let's count from 0, I guess. Because the pin count is 0, your queue contains F1. So this is F0, F1, F2. Now the query says release A, and so the pin count for A goes down, so it also gets unpinned. And therefore, F0 is pushed to the end of the queue. So here, you have F0 is added to the end of the queue. F1 is at the head of the queue. Okay, does that make sense? So now you have 2 frames that actually have pages in them, but their pin counts are 0. Next, you have a request for E. What do? You have to look at the frames. You have to look at the queue of pointers. this queue tells you which frames are actually free, and then take the one from the head. The queue tells you F1 is free. F1 is the second, this one, B. And so what you need to do is overwrite B with the new page E that you have read from disk. It doesn't matter, you just erase that region of memory, set it all to 0, and then read E into there. The dirty bit for B is 0, so that means nobody updated anything. So you're perfectly fine with just pretending as if that region was empty in the first place. Okay, so now your queue of pointers F1 has been evicted because it's now occupied by E, where the pin count is 1. Request for C comes in, the queue has only one entry, the only place you can read C into is the frame there with A in it. But unfortunately, there is an issue now. The dirty bit for that frame has been set to 1. Therefore, you need to flush the contents of that page to its corresponding location on disk. The algorithm, LRU algorithm, tells you this is the only frame you can actually use, but that frame is dirty. Therefore, the page contents of that frame has to be written back to the location of page A on disk. That is how you persist the updates made by the query to A. Once you do that, you can actually delete the contents of the buffer frame and then load in page C from disk. And then you pin it, the pin count goes to 1, the dirty bit goes back to 0 because C is not dirty. A was dirty, but A has been flushed. Once it's flushed, the dirty bit is unset. Okay, so now you're back to dirty bit 0. Every frame is occupied by a page with a pin count of 1. And every page is not dirty. Okay, does this make sense? Any questions? So this is how you work through the algorithm for buffer replacement with a toy example like this. Yes?
What happens if I request fade now? Like when all the 3 of those have a pin count?
Yeah, good question. What happens? The query will be put on a wait queue that is external to the buffer manager, and that query will have to wait until one of these pin counts gets to 0. Okay, so that query will be waiting. It will not execute at all. Okay? Yes?
Is it doing busy waiting?
It depends. Different implementations use different things. Typically, it's not busy waiting. It won't consume any resources. The user will just not see anything happening. Yes?
Is the query queue a part of the buffer management system, or
Is the what?
a part of the buffer management system?
Right. So the query is actually given to the buffer manager, these requests, by a higher level piece of software that's your query processor. Okay?
So the request is being queued.
Yes, the request is being queued. Okay, any other questions? Yes?
Are all queries guaranteed to call release?
Let's see. Yes, if you use the right abstractions when you are issuing queries. When you are doing transaction management, release only matters when there is an update. Like otherwise, if release is not there, then if the query is completed, buffer manager will automatically release it. Okay? But if the query says I don't need this anymore, and then does something else, then you would explicitly say that in your transaction. So we'll get to transaction management later in the course. So for our purposes right now, we can just say release is actually issued to the buffer manager by this query processor. Okay? Any other questions? Yes.
So like before the last step, when we have a frame 0 in the queue pointers, what if like we request for A again?
Now or in the past?
Oh, in the past. Like
Okay, so let me redo this. Tell me where you want to stop.
Yeah.
Okay.
Next.
Release A.
Next.
Okay. Request E.
Yes. And after this, F1 is out, so there's only
F1 is
F0
out.
in the queue, right?
Yes.
And like what happens if we request A again because A is already there?
Yep, good question. A is already there in memory, it's a cache hit, therefore the buffer manager will just return this frame location to the query, but the pin count will get incremented.
For the pointer queue, because A is now like the most recently, or like is in use right now?
Oh no, the replacement only matters when you have to evict something. right? Here you don't have to evict A at all. If you're requesting A after this, A is already in memory. That's your first diamond in your flowchart. It's already in memory. You just return that location, and then you pin it to 1. Okay, does that make sense?
The Q pointer still points to
Yeah.
A, right?
No, the queue will get empty.
Oh, okay.
Because the pin count becomes 1, the queue will become empty. Okay, so this new query that comes in and asks for request A will increment the pin count to 1. Because the pin count is now 1, it will be evicted from the queue. Okay? Yes?
So what if two users use some page like page A here?
Mm-hmm.
So I guess the management system will increment the PC here.
Yes.
But here so one user will write on the page A, and I guess at the beginning these two users will share some page.
Yes.
But later, when some user will modify this page, so what happened?
Good question. We will get to this later in the course when we deal with transaction management and conflicts. For now, assume two users don't update the same page. Okay? When two users update the same page, you have to worry about what lock did the user get. And then you have to worry, are these locks compatible? Okay, so then concurrency control comes into play. So for now, we will not we'll assume that two users do not modify the same page, okay, at the same time. If this page is dirty, let's assume that you're not going to modify it again by another query. Okay? If it's modified by the same query, not a big deal, because the same query owns the dirty bit is basically done by the same query. It could go and update the page again. Okay? Any other questions? Okay, so this is just an illustration to show you how the algorithm works, why it manages memory the way it does, and why it is important to flush things when a request comes and you have to evict a dirty page, why you could get cache hits, like he pointed out. You don't need to go to the disk all the time. That's the point of having buffer pool. Oh, you need something?
Yeah.
Why are you reading up there?
I'm just tired.
Okay. Okay, great. So then you have release C, yeah, so that's down and so on. So now coming to the clock algorithm, which probably the TA talked about, it's basically a variant of the least recently used, wherein you don't have a queue data structure, so you store less information. You still have the same buffer frames, you have n buffer frames. Instead of laying them out as a grid, you imagine them to be on a circle. And that's why it's called a clock, it's a circle. And you have this new piece of metadata that's called the current variable. The current variable takes 1 to n, a value from 1 to n, so it can be imagined as a hand that points to one of these frames. And each frame has a reference bit alongside the pin count and the dirty bit. So essentially the only metadata that is saved here is the frame pointer queue. Instead of having a long queue of frame pointers, all you have is this current variable. Okay? Okay, so how do you find a frame to replace in this algorithm? How did you find a frame to replace in the LRU algorithm? There's a subtle difference here. You have to look at the pin count. If the pin count is greater than 0, then you increment current. That means the clock moves in clockwise fashion. Okay? It goes from 1, 2, 3, 4, n, and then n plus 1 modulo n, which is 1 again. If you reach a page or a frame that has pin count 0, then you have to look at its referenced bit. Notice that the reference bit is a new piece of information that is not there in the LRU. What does the reference bit tell you? The reference bit approximates the recency of eviction or the recency of access. In the LRU algorithm, the queue gives you the recency information. You have a queue of pointers to frames that had PC of 0. But that queue data structure is pretty heavyweight. It's approximated with this reference bit over here. If the reference bit was 1, you set it to 0 and then you move along. Okay, so that's all you do. The reference bit was 1, even though the frame is free, you can actually load it in there. You choose not to load it in there. And that is how the clock approximates the least recently used. You keep doing this over and over until you hit a frame that has both pin count 0 and reference bit 0. then you pick that frame into which you will read the new page. Okay, does that make sense? So it's the reference bit that allows you to approximate the recency information that the queue provides in the LRU algorithm. This is much easier to implement than the LRU algorithm. This does not guarantee that you will replace exactly the least recently used buffer frame. The LRU algorithm obviously guarantees that. That's why it's called the LRU. The clock algorithm does not guarantee you will replace only the least recently used, because you don't have a whole queue to tell you the time information of which one was freed when. All you have is the single bit called the reference bit that approximates that information. It might be the case that some frame that got picked was actually not the least recently used. It could be something that was intermediate. But that's okay. It's just an approximation that's lower overhead for implementation. Does that make sense? Okay? So that's your illustration. I think the TA probably already showed this. So, any questions about LRU or clock and the relationship between them? Yes?
For the MRU, you just need to switch the queue with a stack, right?
I'll get to that. So now, what is a disadvantage? I told you about access patterns. We talked about sequential versus random access when we talked about page layout on disk. LRU is actually a bad algorithm in terms of runtime performance, in terms of the I/O cost, if you repeatedly scan a file. So if you have a file and you're doing an aggregate query, so you scan the file. Now another aggregate query comes in, you scan the file again, top to bottom. When you have that sort of an access pattern where you read the file from top to bottom over and over, LRU is a poor fit. And there's this problem called sequential flooding that explains why it's a poor fit. Like for example, if you're given this number of buffer frames is less than number of pages in a file, that means the file is basically a relation. The relation is so large that it cannot fit into memory. Then every page request costs a disk I/O. Why is that? Let's say you have 3 buffer frames, but then 10 pages in your file. First you access page 1, then page 2, then page 3, then page 4, and then all the way to page 10. By the time you read page 10, what will be in the buffer frames?
8, 9,
7, 8, and 9. And by the time you read 10, 7 will be evicted. And so you'll now have 8, 9, and 10 in your buffer, but then your request asks for page 1 again. And so you will have to read page 1 from disk all over again. Okay, does that make sense? So that is called the sequential flooding problem, where every page request ends up causing disk I/O. There is another replacement policy that is optimized for this sort of problem, and that is your most recently used algorithm. Why is that? So when you read 1, 2, 3, 4, when you read the 4th page, the frame that will get evicted is the one with the page 3. Now when you read the 5th page, 4 will get evicted. When you read the 6th page, 5 will get evicted. By the time you get to 10, 9 will get evicted. And then when you come back to page 1 as the request, it is already in cache. Okay? So the MRU basically avoids the sequential flooding problem for this specific access pattern. Who tells you this access pattern? Not the user. It's the query processing system that tells you the access pattern, because it knows how relational algebra operators behave. It knows how SQL operators behave. Okay, so we'll get to the how query processing works in the next topic, in actually a couple of weeks. Okay, great. Now, random, FIFO, there are other policies. We usually don't use them in relational DBMSs. Clock is probably the most popular. LRU, MRU are also used. Okay? Great. So now there was a question last class about operating system and DBMS. Why not just manage databases as files? Why do we need this special piece of software called the Relational Database Management System? As such, every request to the disk goes through the operating system's file system. The DBMS does not implement its own file system. If you have your file system, like you have a SATA hard disk, and then you have your Linux file systems, a DBMS that's implemented on top will use the same file system as all your other applications. So why not just let the OS handle the database files? Why not just reuse the operating system's buffer management or memory cache management? Well, it again comes back to data access patterns. Only the DBMS, only the relational DBMS understands the data access patterns of relational queries in a fine-grained manner to optimize the access patterns and optimize memory management. Okay? An operating system doesn't have knowledge of relational algebra or queries or SQL. If it does, it's no longer just an operating system. It is your DBMS. Unfortunately, Linux is not a DBMS. Linux is just an operating system. PostgreSQL is a DBMS that sits on top of the OS file system. Okay, so a DBMS is a piece of software. So now when you speak to operating systems people, they'll tell you, oh, database people are just one application. Yes, it's just one application for an OS, but it's one of the most important applications from the OS perspective. People build entire data centers just to store data and query data. There are machines that get sold that run only the DBMS process. No other process apart from that gets run. Like we have Teradata here. They sell giant machines that only have Teradata DBMS run. And managing data is one of the most important applications in computer science. The OS has other applications it runs. Editing your text document, playing video games, listening to music, watching movies. These are all applications for your OS. DBMS is also an application. But banking, insurance, finance, all of these companies, they care much less about watching movies than about managing their customers' data. Okay, so that's why DBMS is a very important special application that optimizes for the access patterns of relational queries. And because it does that, it can do a lot of optimizations. Things like prefetching pages as per the query semantics. We already talked about the sequential flooding problem. How do you know the sequential flooding problem is going to arise? Well, the DBMS knows because it sees an aggregate query. And so it knows the file is going to be accessed in a sequential manner. The OS doesn't know that. It can better interleave I/O and computation. There is something called direct memory access, or DMA. When a page is getting read from disk, the CPU is not sitting idle. The CPU can actually run some computations on another page while the buffer manager is reading a page from disk to RAM. So there's parallelism there that can be interleaved. I/O and computation can run at the same time. And this is only possible because your buffer manager knows which page is getting accessed how, and the query tells you which page is getting loaded, which page is getting computed. Yes?
So if DBMS knows the data access pattern, that means it also knows like how frequently the disk is accessed, right? Like, and then does it mean like DBMS can actually change the scheduling policy based on like how like the hit list or something like that?
Like how hot a page is?
Yeah.
Yes, definitely. That's where your buffer manager helps. If there are pages that are very highly accessed, you can actually have more complex buffer replacement policies that pin pages permanently to buffer memory.
So it's actually changeable, like
It is changeable.
Oh.
The DBMS, I only talked about LRU, clock, and MRU and stuff. There are a dozen different algorithms out there. Commercial relational DBMSs like Oracle or SQL Server probably use more complex policies that take into account these sorts of, this page is getting accessed by many queries, so let us permanently pin this to buffer memory. It will never get flushed, never get evicted. I mean, it can get flushed, but it will never get evicted. So those sorts of more sophisticated policies can be done by the DBMS because it has statistics about how many queries come in, how many queries access this page, and so on. Okay? In many cases in the real world, especially in enterprises, people don't just have a single disk system. There is something called RAID. Does anyone know what RAID stands for? Does anyone know David Patterson? He won the Turing Award this year, if you haven't followed the news. Turing Award is the Nobel Prize of Computing. David Patterson and Randy Katz at Berkeley, they invented RAID. It stands for Redundant Array of, I don't know what the I is, Redundant Array of Independent Disks. Okay, the idea is reliability. In the enterprise world, people typically have multi-disk systems, say 4 disks or 3 disks, and data is actually made redundant. You have copies of data on each disk that is striped out across disks in non-trivial fashions so that if any one disk crashes, the data is not lost. Okay, so there's reliability issues there. If a disk crashes, which actually happens, you could have corruption on the magnetic tape or something like that, data is still available based on the other disks. So there's some coding theory style ideas there for figuring out how do you lay out bits across disk. So the RAID is one of the most popular disk-based systems that allow you to have multiple disks storing data. When you have RAID, different parts of the data are actually replicated on different disks. The DBMS can actually exploit that knowledge and use more parallelism for your queries. Okay, so now if you need a page, that page can be read from one disk instead of the other. So that sort of sophisticated forms of I/O parallelism the DBMS can do because it knows how the pages are related to the queries. Okay, so these are some of the systems level issues that allow the DBMS to provide better efficiency, better runtime performance for relational queries compared to just having a file-based approach that an OS would do. Okay? If the OS, there's nothing preventing the OS from doing all this. It just means the OS will have to re-implement the DBMS from scratch. Okay? Anything else? I think we should probably. Yeah.
So the DBMS basically, I mean, forbidden the replacement algorithm on file system. And
What?
if using, I mean, does it forbid the replace algorithm of the OS file system and using its own page replacement algorithms?
Yes. The DBMS buffer replacement is completely different from the OS buffer replacement. They can be the same. They can be different. Okay? Does that make sense?
But here, DBMS set on the tops of the file system.
Yes, it sits on top of the file system because every request that goes to the disk goes through the system calls, the file system calls. That's the only way it happens. So the OS might also cache some stuff if it has some chunk of memory. So you have a 32 gig machine, you give the DBMS only 16 gig. The OS might use 10 gig for its own cache. It might actually cache some of parts of the files. DBMS will not be able to know that. It will not be able to use that. Therefore, it is recommended that you give most of the RAM to the DBMS buffer pool.
But does the DBMS know the, how to say, the physical address?
It does not know the physical address on disk, only the OS knows that.